In this video, we are going to look at word embeddings. So in machine learning, if we are working with text, for example, it's important that we convert text to numbers that then can be used for training a model. And to convert text to numbers, there are a couple of ways. One is one hot encoding. Let's say we have this sentence, the cat sat on the mat. This can be converted into numbers as shown here, where we have each value. For example, we have the columns, unique words, cat, mat, on, sat, the, and then if we have, let's say, a word the that comes in, then wherever this word matches, we'll have a 1, all others values will be 0. So we have a vector where we have all of the zeros and then 1. And if we have another word cat, and in this case, then the cat would have the value of 1, others will be a value of 0, and so on. So what this creates is a matrix of ones and zeros, and for most part, this matrix is empty. It has all 0 values. And so this is not the most memory efficient way to do it. There's another way, as listed here. We can encode each word with a unique number. For example, we can give the numbers as shown here. We can assign a number 1 to cat, 2 to mat, and so on. So we have this vector where we have converted the text, the cat sat on the mat, into a vector of integers. However, this particular method also has its limitations because it can be challenging for a model to interpret these numbers. And so there's another way, which is called word embeddings. What this does is it gives the each word a set of floating point values uh, that can that would let's say position a word in a particular feature space. So in this case, what we have is a 4-dimensional embedding. So each word has 4 different values of float, and so if we plot these points in a graph, then we will be able to see which words are similar, and the similar words would be closer, and these values, they are trained by the model as during the training process. And so what we are essentially doing is we are uh, trying to find the optimal uh, values for these embeddings during the training process. Back here in the Colab notebook, we'll now start to write the code. And again, the code is directly from the docs. Here is the link for that. And I'll be copying the code from the docs and kind of try to explain what the lines of code are doing. So here, first we'll go ahead and import all the libraries. So we have import IO, import OS, import, and those are the ones that we'll be using to put the data in directories, and then put import RE for regular expression, and that we'll use for pre-processing. Import shu till, then we have import string, import TensorFlow as tf, then from TensorFlow dot keras import sequential. So we'll build a sequential model, sequential, and then from TensorFlow dot keras dot layers import dense embedding global average pooling 1D, and another we'll import is from TensorFlow dot keras dot layers import text vectorization. Okay, so these are the libraries that we need. Now what we'll do is we'll download the IMDB dataset. So let's do that. Download the IMDB dataset. And what this dataset has are the reviews for movies, and they have labels of zeros and ones if the review is positive or negative. And this, what we'll be doing is a sentiment analysis. So get the dataset, we'll use URL here https ai.stanford.edu, and then here we have a MAAS data sentiment ACL IMDB with a capital I underscore VI v1.tar.gz. So that's the file, and to get that file we can write dataset is equal to tf.keras.utils.get file and specify the name ACL IMDB underscore vi dot tar dot gz URL, and then untar is equal to true, cache underscore dir is equal to period, and then cache underscore sub dir is equal to just blank there, and we can run this. And once we have that, then we can look at the path for the data sets. While that is running, we can go ahead and type this dataset underscore dir is equal to os.path.join os.path.dir name dataset, and we have ACL IMDB, and then we can list os.list dir datasets and dataset underscore dir, and this should list the dataset, the contents of the directory. And so here we have readme test imdb.vocab imdb.er.text and train, and we can go in here on the left hand side in folder, and here we can see that we have there are additional files that I've run this code earlier, but these are the files we have. We have the train, we have the test, we have the readme, vocab, and err, and within train then we have two folders: positive reviews, negative reviews. And if you were to click on any one of these, so if we click on, let's say, the negative, let's try to open one of the txt files. So here, this is the file. If you open this file on the right hand side, you should be able to see this review that is written. So we have airport 77 starts as a brand new luxury, this, etc., etc. So that's the review. Those are that is the data that we are going to use to train our model on. So let's look at the train directory inside of this notebook. Train underscore dir is equal to os.path.join data set underscore dir train, and here we can list the contents os.list dir train underscore dir, and we see that these are the contents of that directory, same as what we just saw here in the train directory. So we have positive, negative, positive, and other folders in there. And so talking about other folders, what we need to do is remove the folders that we do not need for training. So remove dir is equal to os.path.join train underscore dir, and we have unsub, so shutil dot remove tree remove underscore dir. So what we are removing uh, those contents from that particular directory. Now if you go back and look at train, we see that those uh, files or contents with unsub inside of this are not there, except that this one is there, but the others are not. Now with this, then we can start to create our train and validation dataset. And to do that, we can set the batch size. So batch underscore size is equal to 1024, and seed is equal to 123. Now train underscore ds train dataset is equal to tf.keras.utils.text underscore dataset from underscore directory. So that's quite a long string there, but that's what will get us the trained dataset. And here we have ACL IMDB backslash train, sorry, forward slash train, and we have batch underscore size is equal to the batch size that we have specified earlier above, and then we have validation split 0.2. So we have 80-20 split, 80% of the data for train, 20% of the data for validation. And then we have subset is equal to subsets is equal to training, and seed is equal to seed. So that is for the trained data set, and I'm going to copy the code and paste it down here for validation set. So we can say validation data set is equal to everything stays the same, uh, except that we are going to put the name here as validation. So tf.keras.utils.text underscore dataset from directory ACL IMDB forward slash train. Then we have batch size, validation split, and subset name and the speed. When we run this, we should see the output here. We are seeing that there are 20,000 files for training, and there are 5,000 files for validation. So that's the data set we have for our purposes. And we can now take a look at what's inside of this. We already looked at one file directly, and we can do the same here. So we can write a for loop for text underscore batch label underscore batch in train underscore dataset dot take one colon for I in range 5. We can print label underscore batch 1 dot numpy, and then text underscore batch dot numpy, and specify the I here. So in the output now we should be able to see the text. So here we have the text, which is the review that we are going to analyze, and then we have the label on the left hand side if the review is a positive review or the negative review. So 0 indicates the negative review, 1 indicates a positive review. And inside of this, you'll notice that there are these HTML tags, break tags, and we will be writing code to get rid of those tags. Before we do that, there's one point we need to configure, and that is configure the dataset performance. Configure the dataset performance, and for this we are going to use the method in TensorFlow, that is AutoTune. We'll set AutoTune is equal to tf.data.AUTOTUNE, and for train_ds dot cache prefetch buffer size. We are going to set it to auto tune, so the algorithm will automatically pick the buffer size. Validation underscore dataset, again, is it's going to be the same line of code, so I'm going to copy that, put this here, and so this is going to be a validation dataset. Again, this is going to be a validation dataset dot cache prefetch buffer size is equal to auto tune. And once this is done, we are now in a position to write the layers that will go inside of the model. Let's now create an embedding layer. So for this, create using an embedding layer. So as we talked about at the beginning of this video, embedding layer is a layer. It holds the weights for in that particular layer. So these weights are then gradually updated as the training proceeds. And so to create the layer, we can simply say embedding underscore layer is equal to tf.keras.layers.embedding 1000, 5. So what we are trying to do here is we are going to embed a vocabulary, embed a 1000 word vocabulary into 5 dimensions. And to look at how this would function is we can create an artificial data. So let's say result is equal to embedding underscore layer, and we can pass tf.constant, and let's say values 1, 2, and 3, values 1, 2, and 3, and then look at the output result dot numpy. And what we see here in the output is for each of the numbers, here each of the entries, we have 3 entries, and therefore we have these 3 sets of rows, and each row is in 5 dimensions. So 1 is represented by the weights in this very first row with 5 values. So if we again look at, let's copy this, and I'm going to create another row here in the matrix and put all of that inside of another square bracket. Okay. So what we have here is we are passing 2 by 3 tensor in the embedding layer as input. And if you look at the output result dot shape, we see that we have the 2 by 3, which is good, and then we have this additional dimension that is added at the rightmost side, which is 5. That's the embedding we are working with right now. So the embedding vectors are aligned along the new axis, as we see. Now for text processing, what we'll do is we'll pre-process the text. Pre-processing. And the reason why we need to do that in this case
it is pretty simple. We have some of the reviews that are written, they have this HTML tag of break, and we are going to write code to remove that. And for this, we'll create a function. So create a custom standardization function to remove HTML break tags, which is given by this angle bracket br backslash angle bracket. And we can define the function custom underscore standardization, and this will take a input data. And first thing we can do is convert the input data to lowercase. So lowercase is equal to tf.strings.lower input underscore data. And once we have created this to lowercase, we can use the regular expression to remove or replace the lowercase. We can replace the break tags with just a space. So save that in a variable stripped underscore html is equal to tf.strings dot regular expression underscore replace, and we are going to replace lowercase comma the angle bracket break space back forward slash angle bracket, and we are going to replace that with a simple space. And this, then we are going to save, let's save this in another variable s, where we are going to uh, uh, create another replace. So tf dot strings dot regular expression under regex underscore replace, and inside of this we'll use the stripped HTML, and then we are going to look for this syntax. So percentage s, and we are going to put that in quotation and put another percent sign here. re dot escape string dot punctuation, and replace that with nothing but just blank. And in the end, we'll return the string s. So that is the function we have, which is called a custom standardization. Now it's time to set the vocabulary size and the number of words in a sequence. So vocab vocabulary vocab size is equal to, we are setting this to 1000, sorry, 10,000, and then the sequence length, sequence with the E, sequence length is set to 100. Next, what we'll do is we'll create a vectorization layer, text vectorization layer, and what this will do is it will normalize, split, and map strings to integers. So vectorize layer is equal to text vectorization, and inside of this we are going to use standardize is equal to custom standardization that we have above, max underscore tokens is equal to vocab underscore size. Wonder why. Okay, that's good. And then we have output underscore mode is equal to int, and output underscore sequence underscore length is equal to sequence underscore length. Okay, so that's our layer for text vectorization. Missing a comma there. That's so that is done. Next, we can make text only datasets and call adapt to build a vocabulary. Make a text only dataset, no labels, and call adapt to build the vocabulary. So text underscore ds is equal to train underscore train dataset dot map lambda x comma y colon s and vectorize underscore layer dot adapt text underscore ds. And with this, then once this is done, we are ready to create our classification model. And okay, so now we'll go ahead and create a classification model. And in this, we will first set the embedding dimensions. Embedding dimensions is equal to 16. And then we have the model. So model is equal to sequential. And here we inside of this open close parenthesis inside of a list we specify all the layers. So vectorize layer. Then we have embedding vocab size, embedding dimension, name is equal to embedding. Then we have global average pooling one dimension followed by dense layer. So dense 16 activation is equal to ReLU and then dense 1 because we are looking at just a binary outcome there. And what the global average pooling does is it returns a fixed length output vector for each example by averaging over the sequence dimension. And so I'm reading it from the docs. This allows the model to handle input of variable length in the simplest way possible. Okay, so with this, then we are ready to compile the model. Compile and train the model. And for this, we are going to also visualize on TensorBoard, the progress on TensorBoard. So what we will do is create TensorBoard underscore callback is equal to tf.keras.callbacks dot capital T TensorBoard log underscore dir is equal to logs, and then we can compile a model. Model.compile optimizer is equal to Adam loss is equal to tf.keras or losses dot binary cross entropy, and then we have from logits is equal to true. Okay, then we have matrix is equal to accuracy. So that's the model compilation. Model is not defined, so let's see why that is the case. I thought we did run this. Okay, we are good now. Let's now fit the model model dot fit, and we have train underscore ds and then validation underscore data is equal to validation dataset epochs is equal to 15 callbacks is equal to TensorBoard underscore callback. And Let's run this. And as the model is training, we can look at the loss. The loss is 0.6 and the accuracy. So as the model gets trained, the accuracy should increase and the loss should go down. And at least now it is starting to go up. So 0.6, 0.7, and we reached 0.8. And the validation accuracy has also gone up to 0.7 and started out at 0.4. So that is looks like that's the final accuracy we have. We can also look at the model summary. We look at model.summary. We can see what layers we have inside of this. So we have text vectorization, embedding, global average pooling, then the two dense layers. And to look at the tensor board, visualize the tensor board, we can type percent load underscore extension tensor board percentage tensor board two hyphens log dir logs, and this may take a few seconds to load, but we should be able to see the plots for accuracy and loss in once this is launched. Almost there. So okay, so this is the loss that we have. This is the accuracy along with epochs on the x-axis, and then we have the loss. As we can see, it's going down along with the epochs. As the number of epochs increase, the loss goes down, both for validation, that is in the blue line, and train, that's in the train is the orange line. Next, let's look at how we can now, once the model is trained, what we have are the word embeddings that we can save, and to save that we can look at how we can save them. So retrieve retrieve the trained word embeddings and save them to disk. So weights is equal to model.get layer embedding and then dot get underscore weights on close parenthesis 0. So we got the weights there, and the vocab is equal to vectorize layer dot get underscore vocabulary. Okay, and then these we can save it in the files, tab separated files. The out underscore v is equal to io dot open, and we specify the file name vectors dot tsv, and then write encoding is equal to utf-8 like so, and I'm going to copy this and paste it down here, and this is going to be out m. This is the metadata.tsv, and rest stays the same. And we can now use the for loop for index comma word in enumerate vocab. If index is equal to 0, then continue, else vector, and this is because as I'm reading it here in the doc, skip 0 because it's padding. And then we have vector vc is equal to weights index and then out underscore v dot write. Here we specify tab dot join, and inside of join we specify for x in vector. We have string x, we convert it to string, and then we're going to add a new line character right here. So that's for the out underscore v, and then for out underscore m dot write, simply have the word plus a new line character. Okay. And finally, we can close out dot v, and we can close out underscore m. So let's go back, remove that d. Okay, so that's how we should. Okay, index is equal to, there should be another is equal to there. Let's in there. Yep. So this is, wow. So now what we have done is we have created, so that's a type of vectors. Okay. So we have created vectors.tsv, and if we go and look in here, we have this. Let's delete this file. We don't need that. So we have vectors.tsv and metadata.tsv. You click on vectors.tsv, we see that these are the embeddings, and if we look through how many are there in each row, it should be 16 of them in each of this row. So if I copy just that top layer, and uh, just for sake of exercise, we paste it here and simply count how many these are. So we have 1, this 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So these are the 16 values, and it is 16 because up here we specified that the number of embedding dimensions is 16. So that's why we have that. Next, we can also try to save this, download this. So if you type try from google.colab import files.download vectors.tsv, and again files.download metadata.tsv, and then exception pass. So if you run this, then you'll get a prompt to save the 2 files on your computer. So hoping we would see that, but maybe not. So let me try to run this again. Okay. So this, I was hoping we will see that. For some reason, we are not able to see. So we should have seen a pop-up that says where you want to save vectors.tsv and where you want to save metadata.tsv. So that was it for this video. I hope in this video you got some intuition as to how to write a code in TensorFlow for word embedding, that is text analysis. We'll continue this series, and I hope to see you all in the next video. Please like, share, and subscribe. Thank you.